We are Team Dangerous Directivity from Brigham University in Provo, Utah. We're very excited this year to be amongst the finalists in the IEEE APS Student Design Competition. We spent the last year working on our design, which is an educational application to how you can detect angle of arrival within a classroom setting.
Here is a visual representation of our project. We have our transmitter subsystem, which is a microcontroller with a small radio transmitter. It transmits at 915 megahertz, which is within the ISM band. And this signal is then picked up by our receiver subsystem. This consists of 4 ducky antennas in a linear line that are connected to our Cabarrus SDR. This SDR then sends the data to our Raspberry Pi that computes the direction of arrival. The final angle from the direction of arrival is sent to our visualization Raspberry Pi, which then clearly projects the direction that the signal is coming from for the user to see, and will move back and forth accordingly as the user moves around the array. For our transmitter, we decided to go with the Motino from Low Power Lab because it came with the RFM95 chip. This was chosen because our frequency is 915 megahertz, which is in the ISM band, and the RFM95 chip is within the ISM band underneath the 1 watt transmitting power limit. This is the chip here with the antenna added to it. And we have this extra connection so that we can connect it to the battery. The signal that we're transmitting is a simple hello world that transmits 4 times every second, and it gives us a really clear signal of negative 35 dBm.
So when we were choosing how we were going to process the signal of 915 megahertz, we decided on using the Cabarrus SDR. All of us are seniors, so we didn't have much experience designing high-frequency signal processing circuits or PCBs, so we thought software-defined radio would be the best option. And this one has 4 RTLs, and it can detect 915 megahertz. So here's where we plug in the antennas with an SMA cable, and this is then connected to a Raspberry Pi, and the Raspberry Pi runs software that we can first use to synchronize this so that the phase is in sync with each other and all the samples are calibrated. And then we can then set it to operate at 915 megahertz. We can change the FIR filter size, the decimation factor, the gain of the RTLs, and then also we can choose which DOA algorithm we want to use. And we're using the music algorithm as it's one of the best algorithms. And so this little SDR does it all. It takes in the signal, processes it, amplifies it, filters it, decimates it, and then it outputs an angle, which is then used in our visualization system that you'll see next.
So we have 2 Raspberry Pis, and the first Raspberry Pi is connected to the software-defined radio and does all the calculations for the angle. It stores those angles in an HTML file, and then the second Raspberry Pi generates all of the visualization you see based on those angles that are stored. And so there's an Ethernet connection, and a C++ script runs on that second Raspberry Pi to read in all of those angle values into the visualization code. In order to generate the visualization that you see, we are using an open source C++ toolkit called Open Frameworks. The way the code works is after receiving the angle from the software-defined radio, we store that angle in a vector and calculate vectors perpendicular to that direction. That is then used to draw the waves that you see on the projector.
So in designing the antenna array, there were a couple of design decisions that we made. So we had to decide how far apart the antennas were going to be spaced. We decided on half a wavelength. We also tried out a third of a wavelength, but we noticed that the performance is better with half a wavelength, which is traditional for DOA to use that spacing. So this is a copper ground plane. So we chose to use monopole antennas, which need a ground plane. This helps to eliminate multipathing and noise in the signal. The signal doesn't bounce around and hit the antenna multiple times. And we saw that the noise floor without a ground plane was about -5 dB, and with it we can see about -20 dB, -30 dB of the noise floor, which is really good for detecting a nice clean signal. And then we also have this second copper sheet, which is another ground plane. This protects so that when the signal comes in, the projector is right behind it. There's a metal rod, and tables have metal bounces signal really well. But when you've grounded it, it does not. So this helps when the signal's coming in, it does not bounce back off and hit the antennas again. And then we also have it just about a foot off the ground above the SDR, because this also is causing multipathing and some issues with the signal. So we had to elevate it about a foot above the SDR.
With the software-defined radio, there are several different algorithms that we can use to calculate the direction of arrival. After doing some research, we decided on the music algorithm, as it's the most popular and it cuts down on noise and allows for clean angle estimation.
We believe that topics such as beamforming and the calculation of the direction of arrival of an incoming signal are topics that are usually discussed in upper college level courses. However, these topics can be introduced and conceptually understood by younger students in earlier classroom settings. Our system that we have displayed before you can be easily replicated in any classroom setting, given just a couple microcontrollers, a projector, and a screen. We think that this is a way that we can encourage students to pursue STEM-related careers and fields in their study. And this will be a way to introduce these topics at a much younger setting. As can be seen in our real-time example displayed before you, our simple 4-element antenna array is capable of steadily measuring from about 35 degrees to 145 degrees, a total range of just under 120 degrees on either side of the array. The antennas readily discern the incoming signal from several meters away. The code is capable of averaging the angles and outputting the angle to the user. We expect this application to aid classrooms of thousands of students and aspire at an earlier age to pursue STEM fields of study. We'd also like to extend a thank you to our professor, Dr. Warnick, who helped prepare us and give us a lot of good feedback along the way. We also thank our coach, Annette Steed, who helped us keep up with our plans and goals. And we'd like to mention one last team member who wasn't here for the video, but finished the school year in Mongolia. Thank you, Basaikan, for all your help in the prototyping and brainstorming of everything. We're very excited to be able to present this to Singapore at the end of the year, and we thank you judges for considering our APS Student Design Contest submission.